So today, I'll be talking about learning multi-scene absolute pose regression with transformers. This is a joint work with Ron Ferenc and Professor Yossi Keller from Bar-Ilan University. And before we dive into what is camera pose regression and camera pose estimation and how we're going to learn it with transformers, I want to give you a taste of what the kind of research we do at Huawei and Toga Networks, and the applications of camera pose estimation and visual localization. So let's have a look together. Okay, so now that he had a taste, let's go technical. So camera pose estimation is a key problem in computer vision, which amounts to finding the position and orientation of the camera from the captured image. It has applications to virtual and augmented reality, like you just saw, indoor and outdoor navigation, autonomous driving, and many more. Now, in many commercial visual localization systems, this is done using a localization pipeline. So it's based on image retrieval, feature matching, perspective endpoint, and RunSAC for estimating the pose. And this requires a map to be available on a remote server with 3D geotagged information, visual information, and others. In this talk, I'm going to focus on an alternative approach called camera pose regression. And camera pose regression methods basically try to replace this pipeline with an end-to-end learning. So the idea is to train a model to directly regress the pose from the image. This means that absolute pose regressors, or APRs, only require a single forward pass, and the trained weights at inference time. This makes APRs a fast, lightweight, and standalone alternative to localization pipelines. And also they are more robust to the intrinsics of the camera used. But as you all know, there are no free meals, and APRs are also less accurate than localization methods, and they're also trained per scene. Let's take a moment and understand what is the implication of this. So if we want to train and APRs for end scenes, we'll need to train a model per scene and apply it at inference time. Okay, so this is not very scalable. In this work, we propose a transformers-based approach for improving the accuracy of APRs and extending the single scene paradigms for learning multiple scenes in parallel. Our work takes inspiration from recent visual transformers like VIT and DITER. We apply encoders to focus on pose informative features and use decoders to transform scene embeddings into latent pose representations. Let's take a closer look and understand how this works. So given a query image, we apply a convolutional backbone to extract visual features. Similarly to other visual transformers, we project and flatten the activation maps. Now, because camera pose estimation actually involves learning two different properties, position and orientation, we apply a shared encoder at two different resolutions and pass this along to two dedicated transformers. So the activation maps are passed into a position encoder and orientation encoder, which adaptively aggregate them using self-attention. Now, consider the images here on the right. These show the attention heat maps. And you can see that the position encoder attends to blobs and corner-like features, which are intuitively more important for estimating the position, while the orientation encoder here on the bottom attends to elongated lines for doing the orientation estimation. In order to learn end scenes in parallel, we apply two different decoders, again, a position orientation decoders, and they are fed with n scene embeddings, one per scene. And the output represents the latent pose representation per scene. Now, again, if we look at the attention heat maps of each decoder output, we can see that the largest response is corresponding to the actual scene. So here on the right, if, for example, I take an image from the old hospital scene and I visualize the attention, I can see that the largest response is achieved on the second output, which corresponds to the old hospital scene. Finally, we take the decoder's outputs, concatenate them, and pass them along a fully connected layer and a softmax classifier to decide which is the right scene. I then take the corresponding outputs of the decoders in the selected scene and pass them to dedicated regressor heads, which will regress the position and orientation vectors. Our model is trained end-to-end. We use the negative log likelihood loss to learn scene classification, and the learned pose loss for learning pose estimation. The learned pose loss is a loss commonly used in camera pose regression, which basically is an optimal balance, learn the optimal balance between the L2 position loss and the L2 orientation loss. And the parameters you see here represent the task uncertainty. So in order to evaluate our method, we use two very commonly used benchmarks, the Cambridge landmarks dataset and the 7 scene datasets. One is an outdoor dataset, the second is an indoor dataset. And the first thing we did is to compare our method to MSPN, which is the only other multi-scene APR. This method applies a convolutional backbone to index a set of scene-specific weights, and then uses them to regress the scene, to regress the pose. Now, as you can see, our method consistently outperforms MSPN with a significant improvement on the Cambridge landmarks dataset, here shown at the top table. We then said, okay, that's great, but we want to compare ourselves to single scene APRs as well. Our point is to improve the accuracy of APRs. So we compared ourselves to a large collection of state-of-the-art single scene APRs. And as you can see, our method achieves the lowest and best position and orientation errors, achieving the first rank on both the 7 scenes and the Cambridge landmarks datasets. Now, up until now, I discussed about learning multiple scenes from the same dataset. But we ask ourselves, can we go beyond that? Can we learn multiple datasets together? So consider the Cambridge landmarks and the 7 scenes datasets. The Cambridge landmarks is an outdoor dataset captured in the city of Cambridge in the UK. The 7 scenes is an indoor dataset, small scale, captured in an office building. And as you can see, when we train on multi-dataset, so the third row in the table, we achieve similar results to the multi-scene setup, and importantly, surpass state-of-the-art single-scene performance. This is despite the two datasets being very different from each other. In order to evaluate the robustness of our model, we carry ablation studies. We vary on the number of encoder and decoder layers used, on the transformer dimension, and the backbone. These changes have a relatively minor impact on the performance. So consider, for example, a variant of our model with 2 layers shown here at the top left table. It actually achieves a very similar performance to a variant of our model with 6 layers. And again, importantly, maintains state-of-the-art performance. Our model also offers a lightweight solution for camera pose estimation. So even for 1,000 scenes, our memory footprint remains relatively constant, around a few dozens of megabytes. If you compare it to what it would be when we train an APR to do that, we'll need to train 1,000 models, so 1 per scene, and this would take around 5 gigabytes. So in conclusion, we propose a novel transformer-based approach for multi-scene absolute pose regression. We use 2 transformer encoders to focus on pose informative features. So they separately attend to position and orientation informative image cues. And as you saw in the attention heat maps, it actually attends to features that are intuitively more important for each task. We then use two transformer decoders to attend to scene-specific information and represent these scene latent pose representations. Our approach is shown to provide a new state-of-the-art APR accuracy. It outperforms single and multi-scene APRs and can even go beyond multi-scene to multi-data set learning. It demonstrates robustness to specific architecture choices and is fast and scalable. Now, obviously, this is not the end of the road. We have a lot of challenges ahead of us. APRs are still behind cloud-based localization pipelines in terms of accuracy. Those are the localization pipelines I told you about in the beginning. So there are very interesting problems ahead of us. I invite you to check out our paper on the ICCV21 website and our code on GitHub. You can also find some trained model there and play with it. And I'll also like to take this opportunity and invite you to join us at the Huawei Tel Aviv Research Center, Toga Networks. We do some very interesting research and tackle exciting research problems in the field of 3D reconstruction, global localization, and 3D mapping. Feel free to ping me. Thank you for listening and open to hear questions.
Thanks, Yoli. It was very exciting to hear you. It was very interesting. I think the problems you are tackling are point of interest for many use cases, and it was very interesting to see your approach. I have here two questions from the audience, and if there are some more, so we have a little bit of time, so please, if we can allow them. First one, can the absolute post-regression paradigm be extended to relative motion? And then what are the pros and cons in that case, the absolute post-regression?
Okay, so yes, definitely. And there's actually a line of work in this direction. So relative post-regression will take two images instead of one and try to estimate the relative motion between them. And again, the same idea of applying a model and training a model to regress this relative motion is applied here. And this direction actually has advantages because it's generalized better across data sets and it achieves better accuracy. The problem is that you'll either need to, like a sequential acquisition, a bit like in SLAM, you need the previous image, or you need to fetch the image from some database. And this again brings us back to having the need for a remote server and where we want something that is standalone and less depending on Wi-Fi and stuff like that. So pros and cons.
Okay, yeah, all depends on the case. And another question, what is the runtime for your solution with a large number of scenes? Let's take 1,000, for example.
So if you consider, for example, our shallow model that still achieves a very competitive performance, state-of-the-art performance, we're talking about less than 30 milliseconds, which is very competitive, even considering single scene APRs.
Very good, and of course, going to be probably much less within
yes,
the time of your research. So
yes, this is for quantization, TensorRT, and things like that. Yeah, just on.
I just thought, so within 1 year, we're going to see you here discussing the way to make it like 10 times less in runtime. Okay, great. Thank you very much.